Alrighty. Let's get this started. Mitchell, are you here? And then let me look for all this geometry stuff. Red. All right, so from the beginning, is that what we want to do? Like, from day one of the semester? Is that the plan? Because I can do that, and I can do it pretty quickly. I mean, it's been a month, so quickly is anything less than like a couple hours. But we'll get this going. All right, so the first thing you want to know is that in geometry and in life, it's really helpful to know if things are literally the same. And by literally the same, what we mean by that is congruent, okay? It's this word right here, congruent. So congruency is a property of two objects if they're exactly the same. And by exactly the same, what I really mean is this. Something is going to be congruent if it is the same size, the same shape, and has the same angles. So, for instance, this triangle here and this triangle here, if I know that these sides are the same length, that's my little tick mark there, and I know that these sides go together, right? They're paired up, they're the same length. And I know that these sides are the same length. And I know that this angle is the same as, that's the first side and the third side, first side and the third side, this angle. First side and the second side, first side and the second side, their angles match. And I know that the third and the second side, their angles match. Then I know that these two triangles are congruent. And that's a little equal symbol with a little tilde, kind of like in Spanish, right? And that means that they are congruent. Now, we don't use the equal symbol because equal means the same in every possible way. And you'll notice there are some things on here that I'm not requiring to be the same. First of all, these two triangles have a different orientation. Squeeze that on there. Not the same orientation. Let me scoot this over just a smidge. Wasn't thinking of bees in the edge of that. They do not also have the same location. Orientation is the way it's facing, and location is where it's located, right? The spot that it's in space. So obviously they aren't the same location, right? One's on the left, one's on the right. Obviously not the same orientation. One's pointing up, one's pointing down, but we don't care about those things. All we care about is the most important things to us, which are size, shape, and angles. It is the same shape. They're both triangles. It is the same size because all of the sides are paired up in length. And then we have the same angles because all of the angles are paired up in measure. And that's what makes something congruent. Now, to prove that this is congruent, to know for sure that two triangles that you're looking at are the same, that two objects are literally congruent, the same. I'm going to use those interchangeably, the same and congruent, even though obviously they're not the same in every way. There's a lot of work to be done here, right? Just for triangles, which are a pretty simple shape, we had to check 6 different things, 3 sides and 3 angles. And this is incredibly tedious, right? To have to measure all of those out and know for sure. Well, it turns out that there are some postulates, things that we can't prove, but we know must be true and we're taking a leap of faith on, that say that we can check fewer things and we know all the rest given, right? So, for instance, if I know that I have 2 triangles that have 3 pairs of matching sides, I don't have to check the angles. I know that's going to be the same. And I can kind of show you why that is. I cannot prove it because remember, it's a postulate, not a theorem. But I can kind of show you why that is. So here's 3 lengths, right? Let me zoom out. Here's 3 lengths. There is only one possible triangle I can make with these 3 lengths. Only one. You might think, well, sure, you can rearrange them, right? I can make a triangle like this. But you realize very quickly, if I try to make like a 90-degree triangle, this one isn't long enough to reach there, right? It never will be, no matter what angle I make. So the only triangle you can make with this is this triangle. So if I already know that the 3 sides match up with these 3 sides, right? These pens are all the same length. Then I know that these triangles are also going to have the same angles. They're going to be literally the same triangle. They have to be, because there's only one possible triangle you can make with those 3 lengths. So there's a shortcut here. If I know that I have three sides, side, 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 then I know automatically that even the angles will be congruent. I don't know anything about the angles, right? I don't know what they are, but I know that they'll be the same. They'll match up between the two. So this is kind of a shortcut. And again, I can't prove that to you. I can just kind of show examples. And that's why we call this a postulate, right? It's something that it just has to be. And so instead of arguing it, which you're more than welcome to, people have decided to kind of move on and build from it until it's proven false, because we've never been able to answer for sure if that's 100% true or not. It just seems to be that way. It's a leap of faith. All geometry, all math is built on leaps of faith, unfortunately. Or fortunately, if you're like me. I like it. Another shortcut that we have is that if I know that I've got two pairs of sides matched up, right? And I have at least one angle, an angle in between those two sides, matched up, then I know for sure, let me zoom in. Then I know for sure these triangles will be congruent. And we call this postulate side, then an angle, then a side. And the reason we call it side angle side and not ASS is because the angle is in between the two sides, right? And that's what this shows, an angle in between two sides. And so if we have that, we know the triangles will be the same. And the reason for that is simple. If I know this angle here, and I'm able to take two other lengths that I know are the same, right? Like these two lengths right here, and set them at the same angle, I bet your imagination can fill out the rest of the triangle. Let me set this at the same angle. There we go. Your imagination could probably fill out the rest of the triangle. It would be this, right? We don't need to know what this length is. We know it's going to show up because that's the only way we can connect the dots here, right? So if I know what the angle is, if the angle is fixed here, and I know these two sides on either side of it, then I know what triangle I'm talking about, right? It has to be one specific triangle. So if both these triangles have those features, then we know that both these triangles are congruent. They are the same. So side angle side works. Another shortcut, and again, this is much better because I only need to know three things, and I can get all six for free, right? Because then after I know they're congruent, I can go in and mark all the rest of the angles and sides and know that they're the same. So here's two other triangles, poorly drawn. If I have something like this, again, I'll zoom in. One pair of matching angles, two pairs of matching angles, followed by a side, a pair of sides that match. I know these two triangles will be congruent. We call this angle side postulate that says if you have two angles followed by a side, then you know the triangles are congruent. You can also write this backwards, SAA, right? You could read this as a side followed by two angles. That's totally fine, right? It's the same thing. What you can't do, however, is rearrange the letters. You can flip them forward and backwards, but you can't rearrange them. So what do I mean by that? Look at this last one. If I rearrange this, I can spell ass. And your teacher doesn't want you doing that. Not because ass is a bad word, but because ass actually does not work. It's complicated to show, and I don't have my stuff from school to be able to show you it. But it turns out that if you have an angle followed by two sides, it doesn't really set what triangle you have to deal with. It actually gives you two possible triangles that you could be talking about. So you don't know which is which. And so you can't say for sure that it's going to be congruent. So ass actually does not work. Angle, angle, side does. Side, angle, angle does. In those orders, right? You can flip them forward and backwards if you want. That's fine. But in those orders, they work, but the ass does not. Another one that would work is this one. And we call this angle, side, angle. So two angles with a side in between them that match. So we have this angle here and this angle here matching. And again, I'm keeping the orientation and the same for these, but it doesn't have to be, right? They can be flipped. So two angles, and then the side that is in between those angles. So this side right here. If I know that about triangles, then I know for sure what the triangle will be, and I know that I must be talking about the same triangle. So that also works. So basically the things that don't work here, what doesn't work is ass, or its reverse, SSA, right? If it's ass or ass backwards, does not work. It could be two different triangles. And what also does not work is triple angle. Notice we never had a triple angle here. We had triple side. So instead of memorizing all of these, I would just remember that these don't work and any of the other three do, right? So any combination of A and S that isn't AS or triple A, you're fine. There's also a last one, a fifth postulate, and it has to do with just right triangles. And it's actually AS if you look at it, but it only works for right triangles, so it has a special name. So if I have two right triangles, like this, let me zoom in. Oh, actually, I'm already zoomed in. If I have two right triangles, and if they're right triangles, I know that one of their angles is 90, right? So I get that for free. If I have two right triangles, and I know one of the legs and the hypotenuse, which is always the side opposite the 90 degree, right? The hypotenuse is always directly across from the 90-degree angle. It's a little arrow pointing to it. Then I know that this is going to work. And if you look at this, this is angle followed by a side followed by another side. So it is AS. So AS only works for 90-degree triangles, and so we have a special name for it. It's called Hypotenuse-Leg. We have the hypotenuse and we have a leg. And we're good to go. So these are our 5 postulates that are going to help us prove triangles congruent. And our job is to be able to collect enough information to be able to use them, right? To get enough sides or enough angles to be able to prove triangles are congruent without having to check every single side and every single angle. So Mitchell, I've been talking for a little bit now. How do you feel about these concepts? Don't memorize them. Again, just know that AS and AAA don't work and that the rest do. And if you find AS, ask yourself if it's a right triangle, right? Because then it would be HL. How do we feel? How are we feeling right now? This tea's going to be super hot. Good? Okay, great. That's good to know. All right, so I'm going to ask you a question. So what if I had a right triangle like this? Because it says hypotenuse leg, right? What if I had both legs and not the hypotenuse? What if I had two right triangles? And again, they can be in any orientation. I'm just keeping it simple for now. Obviously, they don't look congruent, but looks can be deceiving. Don't go off of looks, go off of what they tell you and what information you have. What if I knew that I had these legs matching, and instead of having a hypotenuse, because if I had that, that's easy, HL, right, hypotenuse leg. What if I had two legs? Would these triangles be congruent? I want you to give it your best shot. You're going to make a lot of mistakes here, but that's okay, because from these mistakes, you're going to learn. Like, more so than any other math, this is a learning opportunity. So I want you to give me your your like, initial intuition, and then we can decide if that intuition is good or bad, and then we can adjust it, right? That's the whole idea. So I just want to know what your instant thoughts are, what you see, and then we can go from there. Kind of like the FedEx arrow, right? Once you see it, you can't unsee it, but until you do and someone shows you it, you probably didn't before. So I need to see if you see it yet, and if you don't see it, I can show you where to look, right? That's the idea. So will these two triangles be congruent? We don't have HL, right? Because we don't have the hypotenuse and a leg, or a hypotenuse and a leg, right? We have two legs. Is this enough to prove that these are the same triangle? What do you think? Oh, the sides were? Yeah, the sauces. Yeah, exactly. You could. Mitchell, killing it. That's what I'm talking about, right? This kid's coming to me for math help, but the kid's a genius. He can think logically. You're absolutely right. If I know what the sides are, I can do PFAG and figure out the third one, right? And if I know all three sides, I win. Yes, absolutely. So we know these are congruent. Now, we can't say side, 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 because technically we don't know the third side, right? I mean, we do, because with Pythagorean theorem, so you can maybe write by Pythagorean theorem, we know the third side. And if we know the third side, then we know all three sides, and therefore it is congruent. And now you're a god, right? And you just did your first flow proof, right? By Pythagorean, I mean, you just did it. You literally wrote it right above me. Beautiful, beautiful. This kid has obviously had me for algebra, and now has had me for geometry. Killing it, man. However, there's a shorter way. Like many things in math, there are multiple ways to do it. But some ways are more efficient than others. You might end up finding a lot of information, like what you said is absolutely true, but it might not be the most efficient, and it might not be relevant, right? You know, like if I ask you what's 2 + 2, and you say, well, the sky is blue, and you wouldn't be wrong. It just might not be helpful for the problem. Now, you're not so far out to say the sky is blue. What you did is not saying the sky is blue. It's not way out there, right? What you did is brilliant. But there is a more efficient way. So remember, we have everything except AS and AAA to prove triangles congruent. So what information do we have? We already have the two sides, right? We already have two sides. Well, what else do we have? We already know that two sides are paired up, right? These sides and these sides. But what else do we have? Exactly. We have that 90 degree in the middle. So HL is important because if we didn't have it, we'd be using AS, and we already said AS doesn't work, right? But here, we can just treat it like any other triangle, right? Side, angle, side. Ta-da! Okay, last thing before we move on from this. I've got two triangles that are congruent, and here's the information that I'm going to give you, and you're going to tell me what proves they're congruent, okay? So let's do this. I'm going to change the orientation here on you. How do I know those two triangles are congruent? Just based off of that information. What postulate would I use? Exactly. Angle, angle, side, or side, angle, angle, right? And it's the reason I ask this question is not because it's a hard question, but sometimes kids will say angle, side, angle because they'll see it in that order. But that's not the order they are in if you go around the triangle, and order matters. So if you start on side, then you could say side, right? Side, and then as you turn, angle. And then as you turn again, from here to another angle, right? Or you could do reverse, right? Angle, starting at the purple, then going to the blue, then going to the side. Obviously, angle, side, angle does not work, right? Because the side is not in between the two angles. Cool. Cool, cool, cool. Although, if you're clever, kind of like you did with Pythagorean theorem, if I know what these two angles are, I know the entire inside of a triangle is 180 degrees, right? So if I know what these two angles are, couldn't I just do 180 minus blue minus purple, right? This angle right here, angle orange, the measure of angle orange, let's go up, will obviously be equal to 180 degrees minus the measure of the purple angle, measure, that's what that little m is for, right? And then minus the measure of the blue angle, right? And isn't this angle also going to be 180 minus the blue minus the purple? So this angle will also be equal to 180, right? That's the whole thing. Minus the measure of the blue, minus the measure of the purple, right? Whatever's left over. So it turns out these two angles will be the same, right? Therefore, you can use a little triangle, 3 dots. That means therefore. We know that this angle over here has the same measure as this angle over here. And if the measures are the same for angles or sides, right? If you measure them and they're the same, that's the same as saying they're congruent. So measures are lengths, right? Which are numbers, and numbers are equal. So I used an equal sign there. If I'm talking about figures, if I'm talking about like specific shapes, like an angle or a side, right? Or a triangle, right? If I say those are the same, what I'm really saying is that they are congruent. That's the difference between congruency and equal, right? Equal goes with numbers, congruency goes with shapes, figures. All right. Cool, 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 cool. All right. Let's do a little bit more logic. Okay? Let's see if you can have a good intuition about this as well. And if you don't, no big deal. Right? If you don't see it yet, that's fine, because you will see it, and that's the point, right? Eventually you will. And once you do, you'll be a god. All right. So here's two triangles. You're like, what? Where are the two triangles? There they are. And I'm going to tell you that you know that this angle and this angle are the same. And you also know that it looks kind of awful. Let's do this. That these two angles are going to be the same. Now, you're right. All we have is two pairs of angles, which is not enough to prove something congruent, right? 3 angles doesn't do it. 2 angles doesn't do it. If you noticed before, No matter what, we always need at least one side, right? 3 sides, 2 sides, one side, right? Doing it without sides doesn't work. However, I'm going to tell you that this triangle here and this triangle here, let's call that triangle ABC. Triangle ABC. And I'm going to tell you that it's congruent to the other triangle. And we're not going to label it yet. And you'll see why. How do I know that these two triangles are congruent? There has to be a side somewhere that I know is congruent, right? There has to be. There's no magic here. How do I know? I love my classes. Giving the answer and asking why. Yeah, exactly. This side is equal to itself, isn't it? Right? It has to be. They share that side. This triangle is using side BC, and this triangle is using side BC. Well, BC is always going to be congruent to itself. We call that the reflexive property. So these two triangles will be the same. Let's label that point D. We know that by angle side, right? Or side angle, whatever order you want to do it in. Just make sure that the side is after the angles, right? Not in between them. And when we say triangles are congruent, it's important to match up their letters. So if you look, angle A clearly goes with angle D. So see that there's an A there? That should match up with D on the other triangle when we write it. The rest is a little tricky, so be careful. Next letter is B. Here's angle B. Now remember, we're talking about angle B on the first triangle, the bottom triangle, right? The one on the left. Not this angle. We're talking about this angle. That's the blue angle, right? The angle here. So on this triangle, B is the blue angle. On the other triangle, the blue angle is angle C. So C is going to go here. C and B are the blue angles on their own triangle. On the first triangle, again, we have angle C, which is the unknown angle. Now, the unknown angle on the other triangle, it's hard to see, but it's actually B. So B will go last. It'll go with this C. That can be a little confusing, right? Make sure, what I would do is I'd cover up. So you're looking at the first triangle first and the second triangle second, and then you can really see clearly what goes with what and not think that B was the unknown angle for the first triangle, right? Because it's kind of two different angles here, right? So that'll go with that. And that's an angle we don't have a measure for, so I'm just going to leave it blank down here. And this order is important because once we know that triangles are congruent, we know that all their other parts are congruent too, right? Because to be congruent means that they're all going to have the same size, the same shape, and the same angles, right? Well, we already know they're both triangles, so same shape. Got it. But now that they're congruent, we also know all the sides will be the same, and all the angles will be the same. So which sides go with which, and which angles go with which? Well, if you look, between the purple and the blue angle on the first triangle is side AB, right? So side AB will be congruent to what side on here? Well, you can use the angles to help you out, right? Between the purple and the blue was AB, right? Between purple and blue here is CD. Now, the reason we write our letters in a specific order is because if you write them in the correct order, like we did here, then you can just look at the letters and know what goes together. Check it out. AB is the first two letters here, right? And it goes with the first two letters here. They're out of order. It's DC instead of CD, but whatever, right? AB is the same as BA. So you can just look at the letters and know. I should also know that BC, the second and third letters, go with CB. BC is congruent to CB. Oh, that makes sense, right? That's the side that we shared, right? I should also know first and third go together. AC congruent to DB, first and third, right? And if you look, AC is this side, and DB is going to be this side. DB, 1, 2, 3. And we already said earlier, AB goes with CD, right? That was from here. So you can match them up and know which ones go with which. We can also do this for the angles. So we know by using our brains, 180 minus the purple minus the blue will get us this one, right? And 180 minus purple minus blue will get us that one. So of course they're going to be the same. But you can just look at the letters and figure this out. This is angle ACB. You could also call it BCA. That C just has to be in the middle because it's the vertex, right? It's where the angle's coming out of. So ACB or BCA, whatever way you want to do it. I'm going to write it ACB because I try to do it in alphabetical when I can. So angle ACB is going to be congruent to. Now let's look at the shapes, right? We can obviously look at the diagram and know which angle, but let's look at the letters, not the shape. Let's look at the letter. ACB is first, third, second. Yeah. First, third, second is DBC. Now follow DBC. Angle DBC. DBC is this one, right? Ta-da! Once the triangles are congruent, we know that all their parts should match up. What we call this is corresponding congruent parts. This is like the mother of all things you're going to need for this year, okay? Like, it's important to have these postulates and everything, right? They're the building blocks. But once you get the triangles congruent, then you get all this other juicy information, which you're going to need to solve problems eventually. And what we call this is CCP. It stands for corresponding, meaning that they go together, right? They match up. That's what corresponding means, like corresponding angles. And then congruent, you know what that means, right? They're going to be the same. And then P stands for parts, the parts of the triangle. So if the triangles are congruent, which they were, we proved that, right? We proved that. Then all of the corresponding parts will be congruent. How do we correspond? Well, we match them up. First and second, first and second. First and third, first and third. Second and third, second and third. Angle-wise, first, third, second, and so on and so forth. Corresponding congruent parts, CCP, can be really important to know what that is and be able to use it. Because oftentimes they won't say, prove these two triangles congruent. They'll say, prove that these two angles are the same. And the way to do that would be to first prove them congruent, and then say, well, now that they're congruent, I know that these angles match up, right, by CCP, corresponding congruent parts. How do you feel about this? Give me a percentage. How do we feel about that? And it should feel better than 50, hopefully, and probably less than 100 because this is your first time really seeing this. So don't feel bad. But if you're above 50, that's really, really good. I mean, we've been talking about this for like, yeah, exactly. We've been talking about this for like maybe 20 minutes. This is like the first week. Okay, so now we need to actually write these proofs, right? We've said them out loud. We've worked through them together. And you kind of did with your Pythagorean theorem thing. Like, I would accept that as a proof. We need to actually get used to writing these. And the way that they have you write them can be in very different forms. So there's 3 different ways to write a proof, and I hate all but one of them. But I don't know if they're going to have you do different kinds. So there's the column proof, which is going to be this. And you're going to have your claim. And then what do they say? Claim and goes with it. Your claim and your, I guess, your reason. So like a claim would be these two triangles are congruent, and your reason would be like because of angle side angle, right? And this is okay. The problem is that what happens is that teachers end up doing this. They'll say like two angles, oh come on, are congruent, and they'll be like fill in the blank. Why? And then you have to go look at the diagram and figure out what it is, and then fill in the blank with whatever vocabulary you remember. And this basically just turns geometry into definitions, the class, right? And I'm not a fan of that. So that's why I try to avoid this, but that's kind of what's going on here. The other thing they can do is like called a, let's see, what is it? I think it's a arrow proof. I'm trying to look in your homework to see what they call it specifically. Hopefully they don't make you do it. Oh, I think it's a flow proof. And flow proofs are like this. So you have like let's do it this way. Angle side angle means that these two triangles are congruent. And if these two triangles are congruent, then by CCP, we know that these two angles on the triangle must be congruent. And if those two angles on that triangle are congruent, pretend we know one of the angles measure. That means one of those angles must measure 80 degrees. And there's our proof. We wanted to prove that that was 80 degrees or something, right? And I don't like this for obvious reason. I feel like it's just very messy to read. And there can be proofs where there's like multiple branches and stuff. And those are kind of nasty. So my question to you is, I see on the homework that in the book it says write a flow proof for some of these, but did you ever have to do anything like this with arrows? Do you remember seeing that anything like that in class? Olivia said she didn't. I can teach it, but I think it's a waste of time. I would much rather teach you the third method, which is basically just column proof without the column. And that's a paragraph proof. Everybody hates them until they realize that they're so much better. That's a P. I can't make P's today. You saw a lot of columns. Yeah, that's typical geometry class. It's baby mode. Here's what I do. I say something like this. Triangle ABC is congruent to triangle DEF by angle side angle. And that by sort of functions as the line for the column, right? Here's my claim, here's my reason. Now, the reason I like paragraph proofs is because I can switch the order. I can say, after this, by vertical angles theorem. Now, we'll talk about that in a second, but remember that's the scissor theorem, right? If I have a cross like an X, then the top angle and the bottom angles will be the same, and the left and the right angles will be the same, right? I can switch the order. Instead of having claim and then reason, I can have reason. By vertical angles theorem, I know that angle ABC is congruent to angle DEF. It's literally the same thing as a column, but the commas and the by allow me to like draw a line. Like I could draw a line through there and make a column proof. It would just be my orders are switched between claim and reason. And I like that because it gives me the freedom to speak fluently, right? I feel like this flows a lot better than triangle ABC is congruent to triangle DEF by ASA. Angle this is congruent to angle that by vertical angles, right? It feels very choppy. I'd much rather speak like this. Triangle ABC is congruent to triangle DEF by angle side angle. By vertical angles theorem, I know that triangle ABC is congruent, or sorry, angle ABC is congruent to angle DEF. Therefore, let's say, I don't know where I'm going with this, but I could then say therefore like side AB is congruent to side DE by corresponding congruent parts. And then I'm done with my proof. Again, you could just draw a line through here and put it into column proof, but what you can't do as a teacher and what you can't do as a student is have this be hunt for the thing, right? So two angles are congruent. Okay, well, if two angles are congruent, I know it's either vertical angles or there's something with like alternate interior angles. Okay, look at the diagram, look for the definition, right? And I don't like that because it doesn't require any thinking, and it doesn't require you to like actually like put together an argument. The argument's already there for you and you're just filling in the blank. So I hope it's okay, and you can tell me if it's not, that I write like this. And then if you want to convert it to column proof, you can just kind of draw a line between here. There's your column. And you can think about which one's the claim, which one's the reason, right? By ASA, well, that's clearly the reason, right? By vertical angles, that's clearly the reason. By CCP, that's clearly the reason. Up to you. You want to do some? From the book? I love teaching geometry. This is like semester 2 is so much better than semester 1. I love proofs. I know most kids hate them, but most kids come out of my class really liking them. All right, so here's what I'm going to do. I'm going to flip over to this. Hopefully this works. It did. Wonderful. All right, so we're going to talk about this real quick, which is not really proofs. This is stupid. This is so annoying that we have to do it. But I guess it's somewhat useful to look at once. I don't think it's useful to look at multiple times. So what they do is they give you these two triangles that are congruent. Or, sorry, they give you these two triangles and they want you to prove whether they're congruent or not. And here are the coordinates. Now you might think, oh my god, coordinates, we gotta bust out a coordinate plane and draw them all up. No. No, please God, no, don't do that. Here's what we're gonna do instead. So I know that I've got two triangles. I've got triangle JKL. J has a point at negative 3, 2. K is a point at negative 7, 4. And L, which I guess I'll squeeze up here, is going to be at negative 1, 9. I'm just copying down the problem. And then we have a triangle FGH. F is at 2, 3. G is at 4, 7. And H is at 9, 1. And we want to know if these triangles are congruent. Now, unless there's like a clear 90-degree angle, like imagine a coordinate plane, right? I have two dots right above each other and a dot here. That's clearly a 90-degree angle. But anything else, like unless we bust out with a protractor to measure it, we're not going to know any angles. So the real question is, when we plot these points, will they make all the sides congruent? Right? Will all the sides be the same length? Now, Mitchell, what did you learn first semester? And hopefully you learned it. I hope you remember. It's been a while. That helps you figure out the length of something. What do we know that we can use to figure out the length between 2 points? Boom. And distance formula is the same thing as what? What's distance formula the same thing as? Right. Let me re-ask the question. What's it connected to? What other thing do we know that distance formula is connected to? Like, where do we get distance formula from? There was a portfolio thing written about it that you had to connect two things. Distance formula is the same as the what? And I hate these types of questions because it's like, guess the right answer, right? Fill in the blank. If you don't know it, that's okay. I'm just trying to see if you do remember it. It's okay if you don't. Distance formula is the same as. It's okay. So if I have, let's just talk in generalities then. Talk about this first. So if I have 2 points on a coordinate plane, right? Here are my 2 points. And I want to figure out how far they are apart, the distance, right? Distance formula. Well, if I have a coordinate plane, I know the coordinates of these dots, right? Some x value, some y values, right? It's the x-axis, the y-axis, right? Whatever those numbers are. The x values, the distance between them is this red line. And the distance between the y values is this red line. And those two lines are perfectly vertical and perfectly horizontal, which means it's a 90-degree angle. So very quickly, I now have a right triangle. The distance, remember, distance is subtraction. x2 minus x1. Whatever these numbers are subtracted, right? If that's 10 and that's 2, the distance is 8, right? Because 10 minus 2 is 8, so that distance would be 8. And to figure out the distance here, I'd subtract these guys, right? If that's 12 and that's 4, let's do different numbers. If that's 12 and that's 6, right? The distance apart would be 6. So all I have to do is subtract those two numbers and I figure out the distance. And then you said earlier, if I know the side lengths and it's a 90-degree triangle, I can do p-thag to figure out the rest, right? So I can take the distance here, right? Whatever that distance is, and I can do p-thag with it to figure out the purple length, right? Let's call that side C. There's side C, length C. And I can take the distance here, right? Whatever that number ends up being. And I can do p-thag with it, right? If I knew that this distance was like 10 and 2, so that's an 8, I'd put an 8 in here, right? It's whatever 10 minus 2 is. And if this is 12 and 6, right, 12 and 6, then I can just do 12 minus 6 here and get 6. So I've got 8 squared plus 6 squared equals whatever this side is squared. Is this coming back to you a little bit or no? How do you feel about that? And of course, we want to figure out regular C, not C squared. So we have to root both sides. Rooting this side gets rid of the square. Rooting this side does not cancel those. We've talked about that before. And there's distance formula. It's just Pythagorean theorem. Something squared plus something squared equals C squared. Right? It's just p-thag. That's all it is. That's where it comes from. So all we have to do to figure out if these triangles all have the same sides is do p-thag with all of these. Now, you could do distance formula and say, like, pick J and K. Ignore everything else. And you plug in the X's, you plug in the Y's, right? And you plug it in, and hopefully you don't goof up this. Look, we know that distance formula is the same thing as Pythagorean theorem. So the distance between J and K That's going to be the horizontal distance squared. Horizontal distance is the x values, right? It'll be this part of the triangle, right? Between them. X values. The distance between -3 and -7. How far are they apart? How far is -3 from -7? Don't think subtraction. Think, how far are they apart? -3 from -7. How far? What's the distance there? How far is -3 from -7? Yeah, they're 4 apart. -4, +4 doesn't matter, right? Because we're talking about distance, not direction, right? So there's 4 squared. Fun game to play outside. How far is 2 apart from 4? Now, again, you could plug them in and you do 4 minus 2 and you get 2, right? But if you just think distance, you don't have to do subtraction, then you won't goof this up and say it's 10, right? 4 and 2, how far are they apart? Because that's all this is asking. How far are the x's apart? How far are the y's apart? Because distance is subtraction, right? How far is 4 from 2? I know, I'm making you type. 2 squared. And then we root, because we want to find the distance, not c squared. We want to find, you know, c. And so 16 plus 4 is 20. So root 20. Let's do the distance between K and L. Whoops, no line needed because we're talking about measure, not the figure. It will be a segment, but we're talking about its measure, so we don't use the line on top. So K and L. Well, I'm getting a beep on Discord. All right, so what's the distance between -7 and -1? Well, 6, of course. What's the distance between 4 and 9? 5. So the length of KL will be 36 plus 25. That's 30 plus 20, which is 50. 6 plus 5 is 11, so 61. Gross number doesn't come out nicely, right? Like root 64 would work, so that would be 8. This is a little bit less than 8, right? Because root 64 is 8. This must be a little bit less. And then JL is the last combination, right? I did JK, I did KL. Now we're doing JL. Much easier than plugging into the formula. Just thinking about what the formula means. -3 and -1 are separated by 2. 2 and 9 are separated by 7. 4 plus 49 is 53. Now the question is, when we do it here, will they match up with these? Right? So there's our first triangle. FG. We want to do GH. And we want to do FH. Okay. So again, just to color coordinate, separated by 2, separated by 5, and then separated by 7. The distance between 3 and 7 is 4. The distance between 7 and 1 is 6. The distance between 3 and 1 is 2. And if you look, 4 squared, 2 squared, 5 squared, 6 squared, 7 squared, 2 squared. They're going to be the same, aren't they? And in the same order. So yes, these 3 triangles are congruent because all 3 sides match up, right? These sides are congruent. So JK and FG. I know KL and GH are congruent. And I know that JL and FH are congruent. So if I were to write a congruency statement, I would say triangle. Let's do this one in alphabetical order. JKL must be congruent to triangle. We said JK must go with FG. So JK, FG. And of course, the last letter must be H. So yeah, they're in alphabetical order. How you feel? Really gross problem, but actually not that bad once you know that distance formula is just Pythagorean theorem. Imagine plugging all those into this instead of just knowing that this means how far are they apart, right? No thinking involved. At least no hard thinking. I imagine that you have the ability to do that for the rest of these if you want, right? But like, let's not and say we did. Let's do an actual proof. We've covered the first like 3 weeks or two weeks or so in about like less than an hour. So it says write a flow proof for number 14. 14 is kind of advanced. They didn't ask you to do that one, obviously, but we'll come back to that. I typically don't make you guys do those until the second set of things, which we would be into right now, but obviously I'm not teaching. Right, so let's look at number 16. And then, of course, they did it because it's a column proof, right? Probably not because this is too hard, but because this is a column proof, and they want you to do a column proof. But we're going to do a paragraph proof, and you can convert it if you want. So I'm going to copy this down, and we're going to go from there. So we have 3 triangles. And you're like, what, 3 triangles? Like the FedEx arrow, once you see it, you won't unsee it. There's triangle 1, and then there's triangle 2 and 3, right? Left side, right side. Seeing it is really half the battle in math, but especially in geometry. Okay, so they gave us that CDE, triangle CDE, is isosceles. So what I'm going to write is given triangle CDE is so isosceles. Iso means the same, right? Like isometric, right? Same length is isometric. Isosceles means, I think scalese means 2. So 2 are the same, 2 sides are the same. I think that's what that means. It's been a while. Normally I'd look this up if I had prepared class. Bless you. So 2 sides are the same. And little ampersand symbol. And G is the midpoint of CE. So given that, here's what we know. Given that, here's what we know. Well, if CDE is isosceles, 2 sides must be the same. Which 2 sides, it doesn't specify, but I suppose in the drawing it does. It says that it's these 2 sides. Okay, so they gave us that. So we know that CD is congruent to DE. So because it's isosceles, I know this. So there's my reason, there's my statement, right? My claim, right? These 2 are congruent. And then it's kind of a 2-for-1 here. And then I know that this is the midpoint. G is the midpoint of CE. So Mitchell, again, if you don't know, it's no big deal. I'm just trying to see what your initial, thoughts are. If G is the midpoint, what does that tell us about our diagram? Like what on our diagram, what more information do we get from that? If G is the midpoint of CE, so that's the midpoint, what must that mean about our diagram? What else can we add to our diagram? If you don't know, that's okay. You haven't been taught this yet. Or at least not by me. Side of CE. Kind of. Yeah, you're definitely onto something. Words are hard, math is easy. So the math you're excellent at, let's just change your words. So if G is the middle, doesn't that mean that CG and GE must be the same, right? If that's the middle point, then it cuts this in half, right? And these 2 halves will be equal. How do you feel about that? Are you feeling okay about that? Does that make sense? Right, if G is the middle, then these 2 sides are equal. Yeah, okay, cool. Again, once you see it. Okay, and that's all they give us. So how do you prove, that's what they want. They say they want you to prove that this triangle on the left is congruent to this triangle on the right. Well, either we need to find some angles here, or we need to find another side, right? Because just 2 sides is not enough to get it done. And here's the thing. If we find another angle, remember, it can't be AS. It can't be these angles, right? Because then we'd have ASS. That doesn't work. It can't be these angles, because then we'd have ASS. That doesn't work. So we'd have to find these angles somehow, right? So probably not going to be the angles. What do you see? I'm throwing a curveball, but I tipped my pitch earlier. So I deem it fair. Let's see if you see it. If you don't, that's okay. Eventually you will. How are we going to prove these triangles congruent? Ooh, see, that's a really good assumption. That's a really good assumption. I knew you'd say that. And it is an assumption. We don't know that they're right triangles. It looks like this line goes straight up and down, but in reality, that could just be my drawing of it. Remember, it's a triangle. It could be something like this. We do know that whatever these two angles are, they do have to add up to 180, right? So they could be 90 and 90, but they could also be like 180, right? Or they could be 140 and 40, or they could be 160 and 20, right? So we don't know for sure. We don't know for sure. However, I will tell you that if this is in the middle and it's dropping straight down, it will end up being 90. You'll learn that later. But we have no way of proving that now, right? It just looks like it should be. Right? Because obviously this is not in the middle to create this. Right? If it's in the middle, it will end up being 90. Exactly. That's the much easier way. So eventually you'll be able to prove that that has to be 90. And in fact, we'll do it now. We'll do it now. So DG is congruent to itself. Seems kind of silly to mark it like that, but it's true. So what we say is by shared side is what I write. So I'll say by shared side, your teacher will want you to write this, the reflexive property. I don't like using the reflexive property because all it's saying is that, look, anything will be congruent to itself. And I feel like that's just a waste of time to write if you're going to write reflexive property, right? Of course, we know that. DG is congruent to itself. It should be almost a given, right? But shared side kind of tells you really what's going on, right? These two triangles are sharing that side, which is why they must be the same. It's not because there's some property that's like, a magic rule. And it's like, aha! It's logic, right? They're the same. So I always write by shared side. Your teacher will want you to write by reflexive property. But whenever you have two things that are equal to each other and they're literally the same thing, that's the reflexive property. This works with angles. This works with sides. Here we're using sides. So we know that. So now I've got three sides. So I'm going to write by side, side, side. I know that triangle on the left, let's do that in alphabetical, CDG, will be congruent to the triangle on the right. So if we look, C is our first letter. It's the one side and the double side, right? One side and two side. If we go over here, one side and two side is E. So C and E go together. D on the left side triangle is 1 and 3. If we go to the right side triangle, we have 1 and 3 as well. So D goes with itself. That makes sense. And G is 2 and 3 on the left side. It's also 2 and 3 on the right side. So they go together. G goes with itself as well. Which makes sense because we said DG goes with itself, right? Right? They should match up. Cool. And now we did it. We proved it. And what you normally do at this point is you either write Q dot E dot D dot, which is QED, and it's Latin for essentially the proofs in the pudding, right? There's my proof. My proof is done. What I like doing is the other thing, which is a little more modern. By modern, I mean like 300 years old, is doing a little box at the end, kind of like boxing your answer, and that lets you know the proof's done. I go a little bit further. I started doing this at my last school that I was teaching at. We do 2 boxes for swag box, deuces. But that's just me. Any student that does proofs, you know they had me as a teacher if they do that when they end their proofs. And that's it. How do you feel about this, right? We know they're isosceles, so we have these 2 sides. We know G's the midpoint, so we know those sides are equal because they're halves, right? They're halves of the whole thing. We know that side because it's shared, right? It has to be congruent to itself. So by 3 sides, we have that they're congruent. How do you feel? Give me a percentage. Because I want to go a little bit further with this than the book actually went and do one more thing. Kind of go back and prove what you were saying. Okay, it looks like a lot, but it's not. You'll get used to it. Most of this right here was given to you. We got from it being isosceles that these 2 sides are the same. That's pretty good. And because this is the midpoint, we got those 2 sides are the same. All you had to do was see that they shared a side. And then by 3 sides, you win, right? 1 side, 2 sides, 3 sides, boom, we win. And that's pretty good for your first real go of it, Mitchell. You said that you think those are going to be 90. And it turns out we can prove that now. Because we know these 2 triangles are congruent, right? We now know that they're congruent. So their angles and sides should match, correct? So look at angle CGD. CGD is first, third, second. So let's talk about that angle. angle CGD should be congruent to angle first, third, second, GD. First, third, second. So these two angles are the same. Now, didn't earlier we say that whatever those two angles are, they have to add up to 180? So I have the measure of the red angle plus the measure of the red angle. They're both the same, right? Should equal 180. Well, that's just 2 times the measure of the red angle. Whoops. And that should equal 180. That means the measure of the red angle has to be 90, right? Only 90 plus itself can get you 180, right? If they're both equal, which we proved they are, right? If both these measures are equal, these angles, if this is the same as that, well, and they have to add up to 180, well, then they both have to be 90, right? 90 and 90 is the only way to have them both be the same and add up to 180. So it turns out you were right about your assumption. We just couldn't prove it yet. So you kind of found out your own theorem, the Mitchell theorem. If a triangle is divided by a line from its vertex, one of its vertices, to the opposite midpoint, then that line hits the opposite side at 90 degrees. There's your theorem. If a line connects the vertice to a midpoint in a triangle, then that line must hit at 90 degrees. The Mitchell theorem. And it's a theorem because it's kind of like the reason we call it a theorem, not a postulate, is because we can prove it, right? We just did. We just did. Cool. That wasn't what they wanted us to do, but we went a little bit further. Let's do another one. So 18 is a little weird. They give you like a circle. Circles are weird, man. And they give you this chord. A chord is just a line that connects one end of the circle to the other. Obviously, a chord you're really familiar with is the diameter, right? That's a special chord. It's the biggest chord in a circle. They give you the center, which I'm assuming is, they give us this, which will be the center of the circle. And they give us 2 radii. And of course, radii are always equal. And then they give us this. So here's what they say. This is point A, this is point E, this is point G, and that's point C. So they say this, given that AC is congruent to GC. So they gave us that, AC and GC, right, from the diagram. And EC bisects, this is really important, we need to talk about this, bisects AG. Okay, so a couple things. EC is a line segment. It's this line segment, yeah? And it's saying it bisects. Bisect means this. Bi meaning 2. Sect, like sectum sempra in Harry Potter, means cut. Dissect, right? Dissect means to cut up a bunch. Bisect means to cut in half. So this line cuts something in half. What is this cutting in half? It's cutting in half AG. So it's taking AG and it's cutting it in half. So if EC cuts AG in half, then that tells us this, right? It's almost like saying E's the midpoint, right? That's another way of saying it. CE bisects AG, so it cuts AG in half, or E is the midpoint, right? Same thing. So therefore, we can say AE congruent to GE. Cool. So they gave us that. Great. Phenomenal. And they also said this, which implies that. You can say therefore or whatever you want. I just like using therefore when I can. So our job is to prove that this triangle and this triangle are congruent. So how are we going to do that? We've got 2 sides already, right? We've got this pair of sides taken care of, and we've just got from that bisection, right, that these are congruent. So we have 2 sides taken care of that are paired up. What else can we do? Yeah, exactly. Right, shared side. Which your teacher's going to want you to say reflexive property, right? Like reflex. It's kind of supposed to be reflection, right? The same on both sides, but they use reflex instead of reflect, right? So we know that EC is congruent to itself by shared side. Again, reflexive property. And now we've got three sides, right? So therefore, by side, side, side. Again, you don't have to write therefore. I'm just, that's just how I speak, so that's what I'm writing. I know that triangle. Let's do the top triangle first, and I'll write it in alphabetical order. ACE. Congruent to. Again, make sure you match up your letters here. A is made up of the one side and the two sides. So if I go to the other triangle, one side and two side is G. C is our next letter. It's made up of, on the first triangle, the top triangle, right? First side and third side. First side and third side is C, so it goes with itself. And then E is made up of second and third. It'll go with second and third, which is also itself. Which makes sense, right? Didn't we say earlier by Mitchell's theorem that if a line goes from a vertex to the midpoint, which is essentially what E is, right? Then that line will be 90 on both, right? So it makes sense E would go with E. Ooh, time to ban. We haven't had to bust out the ban hammer in a while. There we go. Although you're a mod, I should have you ban him. All right. And so now we know the two triangles are congruent by side, side, side. We also know by Mitchell's theorem that these two are 90, but again, we could just go forward and say, if we wanted to, by CCP, since we know the triangles are congruent, E is going to go with E. Angle E is AEC. Will be congruent with AEC, GEC. GEC, right? So if they wanted you to prove those are both 90, you could just say, look, they're both congruent, and since they have to add up to 80 or 180, they're both going to be 90. But they didn't want that. They wanted you to end the proof here. So swag box after that. How'd you feel about that one? Again, if you want to draw like a line down the middle, here's our reasoning, right? Right here. Reason claim, reason claim, reason claim. And then we just wrote the given. Reason, claim, claim, reason, reason, claim. How do you feel about that, Mitchell? Hope I didn't lose you. I didn't ban you, did I? Feeling good. Excellent. Okay. So by now, I think you're seeing like shared side is a pretty big freaking deal, right? You should be looking for shared sides. And to be clear, a shared side is shared between the two triangles like EC is, right? Like we saw earlier, this is a shared side, right? Just because two sides are congruent does not mean they're shared, right? They're congruent sides, but they're not shared. They're not overlapping, right? Okay. So let's look at some harder ones because these are baby mode now. Actually, let's do baby mode real quick without writing it down to save some time. So look at this. Not the cat. This. All right. These four right here. This is super simple. They're not even asking you to write the proof. How are these two triangles congruent? 22. What would you use to say the two triangles are congruent? What postulate? right? Because of shared side, right? Again, if you were doing a proof, like in my class, you'd be like, okay, there's shared side here, and you'd show your reasoning. Here, it's not even, it's baby mode, right? Side, side, side. 23. Congruent or not? And if so, what's the thing we'd use? First of all, no shared sides, right? Because they're not overlapping. So all the information we have there is all the information we have there. What do you feel about 23? Side angle side? That's a good guess. But is the angle in between the two sides? It's not, is it? It's after the two sides. Do you see that? SSA. What does SSA spell backwards? What does SSA spell backwards? Bum, bum, bum. Not allowed to use ass or ass backwards. Unless this angle right here is 90 for both of them, then we could use HL, right? Because then this side here would be a hypotenuse. But unless that's 90, we don't know that they're congruent. It doesn't work. It's not enough. And again, it's a postulate, so it's hard to show you that it doesn't work. But basically, these triangles could be two different triangles. There's two options. It's not, you know, they could be any triangle, but there's two options, so there just isn't enough. It's just so close, but not quite. So we can't. We don't know whether they're congruent or not. They could be, right? If both those are 90, yeah, sure, right? If both these angles, if both these angles are 90, they could be, right? But we don't know for sure. Not enough to prove it. Not enough. We don't even know that they aren't congruent, right? They could be, right? They have a lot that matches up. They could be if we knew more information. We just don't know for sure. 24. Do we have enough? And if so, what's the reason? Or right off the bat, like, what do you notice? You know, answer any of those questions. Yeah, exactly. We have the shared side in one angle. That's not enough. Like, and that's a key skill for you to understand when there just isn't enough, right? Because otherwise you stand there sitting there all day and you're just like, oh my god, where is it? Where is it? Why am I not seeing this? But like, there's no more information we can gather, right? You can imagine that like this side, you could stretch it out because they don't tell you it has to be a certain length, right? You could stretch that one out really far and not stretch this one at all, and then those angles would still be the same, but they wouldn't be the same triangle, right? So anything that isn't labeled, imagine stretching it, and if it changes it to a different triangle, well then we don't have enough to conclude, right? If we knew these two sides were the same, then we'd have angle side side. It still wouldn't be enough. That'd be ass, right? So there's a lot that can change here. Not enough. And then for 25, the only thing funnier than 24, how would you solve that one? Like, it is congruent. There's actually two ways to do it. Can you find the two ways that you could prove these triangles are congruent, left side and right side? There's actually two ways. Sorry, had to respond. Side angle side and side side side. Exactly, right? We have side angle side. Notice the angle is in between the sides, so it is SAS, right? It's not ASS. And then we can get the shared side here, and then we've got matching sides, right? Three matching sides. I actually want to look at 25 for a little bit because this is going to preview a theorem that you're going to learn later called the isosceles triangle theorem. So let's look at that just real quick. So if we have this, it turns out that if these two triangles are congruent, which they are by side, angle, side, right? In this scenario, we don't have side, side, side because they're not overlapping anymore. I pull them apart. We don't know for sure those are the same. But we do know they're congruent, so all their sides and angles should match up. Well, if you look, this is the single side and the unknown side, right? So that's going to go with the single side and the unknown side over here. But there's two options, right? Here's single and unknown. Here's single and known. So it could go with this one, or it could go with that one. In fact, it actually goes with both. If you have an isosceles triangle, the angles across from the congruent sides will be the same angle. Always. Always. That's called isosceles triangle theorem. So you get those two angles for free. So if I just gave you this, you would automatically know, since it's isosceles, that these two angles must be congruent. There and there. Turns out. All right, let's look at other stuff. Oop, wrong button. Not this one. Angle S, angle N, E, angle M. All right, so let's just look at this real quick. We're not going to write it down. But look, I have two sides that match, right? RS and PN. So there's a pair of sides, right? One set of sides. I also have another set of sides, RT and MP. And then I also have two more angles. So I have two sides and two angles. That's overkill, right? That's way more than I need. So there should be enough information to get the job done here. Right? Side, angle, side probably is what we're going to use. Because remember, we only had two sides to work with. And there's no overlap. There's no shared side here. So it's probably going to be like side, angle, side. Or, yeah, I guess, or angle, angle, side. Right? Two angles and a side. Two sides and an angle. So yeah, we won't even bother with that. But there's a way to do it. I want to look at this one because I think it's fun. Look at 30. So let's write this down. Write that down, write that down. Do I have that? Do I have that SpongeBob thing on here or do I not?
Write that down, write that down!
I do. All right. So here's the diagram. We have a straight line, because all lines are straight. And then we have two rays that come together to form a 90-degree angle. And these are rays because they don't go on forever in both directions. They only go on forever in one direction. Baby, you light up my world. Need that on soundboard. So we have some angle and some other angle. And we want to know the relationship between these two angles. And there's a lot of different relationships, right? One can be bigger than the other. They can both be equal. They can add up to a certain amount, right? There's lots of ways to talk about relationships between things, not just equal, right? They don't always have to be equal to have a relationship, right? And here's the thing. We know scissor theorem, vertical angles, right? That says whenever we have an X, top and bottom angles will always be the same. So check this out. Whatever angle B is, I know that it's the same angle here. Because that's an X, right? We have two lines hitting each other to form an X, which means cross angles will be the same. So I can say by vertical angles theorem, or scissor theorem, your words, not mine, we know that the measure of angle B, actually it's hard to write this because I don't have any letters, right? I don't have like angle ABC equals DEF, so I guess I won't write that. So by vertical angles theorem, I know those two angles are congruent. By vertical angles theorem over here, I know whatever this angle is, which might be different than B, so I would use a different color. Will be the same here. That's kind of cool. Mitchell, how do you feel about vertical angles there? The X's. Again, you got to make sure they're X's. Like this is not an X. Right? See how it's not two straight lines intersecting? But that clearly is, right? X. X. How do you feel about that so far? By vertical angles, I know whatever that is that. Whatever that is that. Okay. What are the internal angles of a triangle? What do they add up to? The internal angles of a triangle always add up to what? So here's a triangle. Green angle. Blue angle. And that's a 90-degree angle. What do they have to add up to? 180. So guess what? If I subtract 90 from this, I know that the green angle, which is the same as B, right? Plus the blue angle must add up to 90. So that's the relationship. We don't know what they are, right? Because they could be like 45 and 45. They could be 30 and 60. They could be 89 and 1, right? We don't know. The diagram looks like it's 45, 45, but that's, you know, it's just a diagram, right? Somebody just drew this really quickly. But we do know that the relationship is that they add up to 90. So if you look here, that's the answer. We know they both must add up to 90. We don't know what they are, but we know they both add up to 90. Classify a triangle with measures of angles of ratio 3 to 6 to 7. I'm going to skip that one. I did a video on that earlier when I did stuff with Olivia. I don't think you're going to see it, so I'm just going to skip over it. It's a good question, but not that interesting. I thought this one was more interesting. We know B and A have to add up to 90. Have to. Let's look at this. We got all kinds of juicy stuff here. You've got time, Mitchell? I know I'm keeping you kind of long. This is kind of like the heart of it, and then after that, I think like it's just all more of the same. This is stupid. We're not doing this. Oh my god, Olivia and I went over this. This is so dumb. It's a waste of your time. There's some okay questions there. Yeah, I don't think we'll do any of these. You won't need to. Yeah, we just got to do this last page. That's the stuff I worked on with Parker. Okay, cool. Yeah, if you can do these, obviously there's like different ways to set them up, but like you've seen problems that are like find the shared side, right? They'll look different, but they're more or less the same. So here, I don't like this diagram because it looks like it could be an X, but it also might not be, which is why whenever I do stuff, I always write specifically BCD is a line. I'll write something like this. I'll say like line BCD and I'll say line ACE if I want to be sure, like to let you guys know that this is in fact a straight line and that is a straight line. Here, I don't think they are. So know that like scissor theorem doesn't work for that, right? Does not work. You can see that kind of with my scissors, how they're not perfectly straight, right? They curve a little bit. See how if it's not perfectly an X, they're not going to match up, right? All right, so let's talk about these three, and then we'll get you out of here more or less. I think this, hopefully you feel this way. I feel this way, that this should take you like a lot further than you were before. Like you should feel much more confident in what you were doing. It might not be everything you guys have done in class, because again, all I have is what I have. But it should be like, okay, now I see what's going on. Hopefully you feel that way by the time we're done with these three, because these are a little more advanced. So let's do this. So we have two triangles that are connected, and it annoys me because like if you're connecting them and they're not straight lines, then why are we doing it? It's like this essentially, so it's not a perfect X, and they give us all of this. So we have this, and then we have this, and then we have some angles that are the same, and they use like, so for this one they'll use like double angle marks to match up double with double. I like using color a lot better, but it's the same thing, the exact same thing. So this angle will go with this angle. I think it just makes it easier to see things when it's in color. And this angle will go with this angle. Okay, now we can't use vertical angles to get these two. Okay, right? It's not an X. So here's our triangles. This one's not too bad. There's lots of ways to solve it, like most problems in math, especially geometry. So we want to prove these two triangles congruent, this triangle and this triangle. How would you do it? How many ways can you find? In fact, I'll write some out. So side, 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 angle, side, angle, side, angle, 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 side. We're not going to use HL because they're not right triangles. So which one of these can you find? There's lots of ways to do this. Side, 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 obviously, right? We have single, double, and triple. So you could do side, 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 right? What else you got? There's just information overload in this problem. Like, they give you way too much. And since they're congruent, it turns out these two angles will be the same, which is even more annoying that they're not an X. You could arrange this to make them an X. So I guess you could prove that you could make both of these straight lines at the same time. That's kind of cool. Side angle side. Where do you see the side angle side? Like, what angle are you using for the side angle side? Blue or the green? Green, okay. You could also use blue, couldn't you? Right? What about angle side angle? Is that here? I wonder if I should start notating it like this. Side angle side. That's like the 2 and the 3. And this one is like the 1 and the 3. What about angle side angle? I don't know if I like that notation or not. Normally I just use colors, but I didn't end up using colors for the tick marks. What else do you see? Again, seeing it's half the battle, which is why I like doing these exercises. Green to blue is ASA. Yeah, exactly. So in any order, right, we can do green to blue or blue to green. I'm not going to write it twice because it's the same thing, just forward and backwards. Right, and that's the 3 side. What about angle, angle side? This one's the one that's kind of hard to see, but it is there. And there's 2 versions of it. It's just because there's so much extra information. It's not usually the way people see it. We're taking a very easy problem and making it much more interesting, I think, by asking how many ways can you solve it. I guess I'd write it like this. Side, 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 single, double, triple. I just want you to get used to seeing all the different ways, all the different angles, if you will. This one's kind of hard to see. You have to look past some information you don't need. Yeah, exactly. Yeah. Excellent job. So green, ignore this side, blue, right? That's the extra information. It's extraneous. And then we'd have the single side. You could also do the other way around, right? Blue to green, again, skipping that middle. And then instead of using the single side, we'd use the double side, right? Cool. Nice job, kid. I haven't done this in a while. Let me do it. All right, 33. This one. How many ways can you solve a problem like Maria? 90-degree angle. By Mitchell's theorem's converse. That's the other way around. Remember, Mitchell's theorem says if it goes from vertex to the midpoint, then that's 90. I'm going to flip that around. If it's 90, then this must be the midpoint. Just the converse. It flips the order of claim versus reason. So they give us all this, by the way. But obviously, if that's 90, would have gotten that for free by Mitchell's theorem. And then they give us that, I get, the diagram looks really stupid here. They drew this really poorly. But it's these two angles will be the same. I'm not going to color that one in, so it's easier to tell them apart. So how many ways can you prove these two triangles congruent? Oh, by the way, if this is 90, Mitchell, what does this angle have to be here? It has to be 90 by linear pair theorem, right? If two angles are on a line, right? Here's a line, here's two angles, right? If we have something like this and we know this is 90, well, the other half has to add up to 180 with it, so it has to be 90 as well, right? So they only give you that one, but of course we get that one for free by linear pair theorem. Two angles on a line have to add up to 180, so if that's 90, that's 90. What do you see? Yeah. What about angle? What about angle side angle? And I love that you said SSS. That means you saw this, right? Shared side. Do you see angle side angle? Well, I'd hope you'd say you could do all of them, right? We have every single piece of information, right? We have all the matching angles, all the matching sides. Anyone you want. In fact, we can even do HL, right? Hypotenuse and a leg. Hypotenuse and a leg. Because it's a 90 degree. Right? You can literally do everything. Once you see that last side, everything becomes possible. Because you have all the information. Yeah, right? Blue to green, ignore the side in between. Yep, exactly. Right? And then we could do green to blue, ignore the side in between. Yeah. Good. It's clear you're able to see this stuff. That's really good. Now, 34 is a different beast because what it does is it has parallel sides. And so what we have to do is remember back to our transversal stuff that we talked about first semester. But other than that, it's the same problem, right? You're used to seeing a parallelogram like this without them calling it a parallelogram and knowing that we have a shared side, right? So they explicitly call it a parallelogram because it's a four-sided figure with opposite sides parallel. Cool. Oh yeah, sorry, I did this for Olivia too. Turns out they give you that this angle is 90. My bad. Sorry, looks can be deceiving. Yeah, we want to prove these two triangles congruent. So right off the bat, I'm sure you're gonna say that they share a side. So let's label all this and let's actually do the proof. Because they just want you to tell. Because all this problem is asking is like, are they congruent? Yes or no. It doesn't even ask you to say why, which just blows my mind. Like, what a waste of time. Like, sure, right? Sure, they're congruent. Why not? I'm sure there's enough information. The other two had literally everything, right? So for this one, we're actually going to do a proof. So all we have is a side, and we only have one angle, right? We don't even have the pair for it. So we don't even have side and an angle. We just have the side. So here's what I want you to do. Whenever you see parallel lines, I want you to pick a pair. I'll pick the two going up and extend them out. So I'm going to do this to kind of make it easier for you to see. I'm going to extend those. Right? They're parallel. I think it was double parallel. And then we're going to pick one other line. We have three to choose from. And we're going to extend that. And that's going to be our transversal, right? Remember the line that crosses two others? So if I want to get some angles here, I don't want to pick this line because that line is going to get me two angles. It's going to get me this angle and it's going to get me this big angle, right? Both of those combined. So I don't want to pick this and I want to pick that. Because those aren't, this angle right here isn't an angle for a triangle, right? This whole angle right here, right? That's not an angle for a triangle. That's an angle for the parallelogram, right? I want individual small angles. So what I'm going to actually choose is this MP line and extend that. So let's put this down here. And here's our line MP. And that's going to be my transversal, okay? Now, remember from transversals, right? If we have a transversal that's crossing two parallel lines, we have a bunch of congruent angles, right? There's a postulate that we have called the parallel postulate that says whatever this angle is and whatever this angle is, they have to be supplementary, right? They're going to add to 180, right? Well, if I know that these two add to 180 by the parallel postulate, by PP, we know that those add to 180. And by linear pair theorem, right, since it's a straight line, these have to add to 180, right? Let's call that the black angle, the angle we don't know. So by linear pair theorem, the black angle and the green angle must be 180. Therefore, what? Let me pull this back. So Mitchell, look at my logic. These two have to be 180 by parallel postulate, right? If you have two parallel lines cut by a transversal, the same side interior angles will be supplementary. That's a parallel postulate. Linear pair theorem says if I have a line and two angles sitting on it, linear pair, right? Two angles on a line paired up, they have to add to 180, right? They're going to make 180 degrees. What does that tell us? What other connection is here? And this is a very open question, so if you're not sure about it, that's okay. It's probably because I'm not asking it very clearly, because I can't. Because that's how geometry is. It's not a very clear question. We know the relationship between green and blue. We know the relationship between green and black. What's the relationship between black and blue? Maybe that's how I can ask it. Based on these two things. Yeah, right? Blue and green is 180. Something in green is 180. Well, the something is blue, right? Therefore, blue angle and the black angle equal each other, therefore they are congruent. This is the blue angle. And that's the proof for alternate interior angles theorem, right? Alternate interior, alternate being their opposite sides of the transversal, right? And interior, they're inside the parallels. So that proves alternate interior angles, but of course we did that first semester, so all you have to do instead of all of this is say by alternate interior angles theorem, those two angles are congruent. By alternate interior angles, these two angles are congruent, right? These two green angles. So if you go back to our diagram, what are the green and the blue angles? Well, the blue angles are actually this big angle here, right? Because we extended this out. It's an angle that's not even on our diagram, right? But what is interesting are these two green angles, because they're the top parts of these triangles, top and bottom. So I'm going to say, by alternate interior angles theorem, right? Because we have two parallels. There's our transversal. They're inside the parallels. They're opposite sides of this transversal. I know that angle LMP is congruent to angle NPM. For angles, it doesn't matter what order you write the letters in, as long as the vertex is the middle letter, right? LMP, NPM, right? P and M are going to go in the middle. Doesn't matter alphabetical order or matching them up. That's just triangles, okay? And so now I've got these two. Well, what if I chose a different transversal? Like, we talked about those other two lines before, and we said we didn't really want those, but let's go back and do that. What if I did... Oh, actually, let's not even do that. Let's do this. Let's do the other two parallel lines. Let's do that. We'll be consistent. And I use MP again. Well, now by alternate interior angles, I get this angle and this angle, right? I also get these two. But again, this angle isn't real is an angle I've already done, right? Or actually, this angle is not even on the triangle. See how it's too big? Right? It goes outside the triangle. But these two orange angles we get. So by alternate interior angles here, these are alternate interior, here and here. So by the same reasoning, so I'm just going to write another statement. NMP is also congruent to LPM. So by alternate interior angles, I get both these things. Now, even if I knew this last angle here, right, and I kind of do, this has to be 90, right? Because 90 plus green and red, or green and orange, is going to get us 180. Something plus green and orange is 180, right? They're both going to be 90, right? But if I just knew those three angles, that's not enough, right? Because imagine a triangle that has all the same angles as another triangle, but the other triangles is bigger, right? They wouldn't be congruent, right? They'd have the same angles, but they wouldn't be congruent. Triple A is not enough. But luckily, I have this side here. So Mitchell, now that I have this, how do I know that the bottom triangle is congruent to the top triangle? What would you say? What reasoning? What postulate? What postulate could you use to prove these two triangles congruent? I'm gonna have to use that side somehow. We did by shared side MP congruent to itself. Alternate interior, we got those two. Angle, side angle, exactly. And then by, and of course you could flip the order here, but I'm gonna do green angle first. Angle, side, angle, comma, triangle. Let's do the bottom triangle first. We'll do it alphabetical, LMP. I always start my first triangle alphabetical. And then the other triangle, let's match them up. Well, L will have to go with N, right? So it turns out N will also be 90 degrees. That's kind of fun. M in the bottom triangle. Again, be careful here, right? We're talking about this triangle. M in this triangle is the green angle. So it'll go with P in the other triangle. And then P in the bottom triangle is the orange angle. It'll go with M in the top triangle, the other orange angle. Cool. Now, that's all you had to do for this. Prove those two triangles congruent. How did you feel about that? First of all, angle side or alternate interior angles gonna be a thing you're gonna use with parallel lines. Luckily, we knew both sets were parallel, so we could use both to get both sets of angles. If both sets weren't parallel, we wouldn't have been able to do this version and this version, right? Okay, so that's our proof. Swagbox, feeling like a god. What if I told you that this is enough to prove that this shape is actually a rectangle? That I drew it really poorly, and it's actually a rectangle. Here's my reasoning. Or let's do this. How do I know that green and orange have to add up to 90? How do I know that? Remember, this is 90, right? It doesn't look it, but it is. And this is 90. How do I know that green and orange also have to be 90 together? In other words, they are complementary. How do I know that? Turns and doesn't keep going. Oh, I get what you're saying, right? Because it turns here. That's a really good point. That tells me that it has to be less than 180, right? Because if it kept going, it'd be 180, right? But it doesn't say it has to be 90. That just says it has to be less than 180. So that's a good point. So we know it can't be 180, right? How do I know it's exactly 90, though? This put together. And again, the drawing is really misleading, but how do I know that has to be 90? And if you don't know, that's okay. This is advanced. Hey, this is stuff that we do later in class. But once you see it, it can really help you out. There's two ways to look at this problem. There's big picture, which is looking at it like a four-sided shape, and there's small picture, which is just looking at individual triangles, right? I want you to look at it small picture. How do I know orange and green are going to be 90? All about perspective. That's what math is all about, perspective, and learning others' perspectives, learning how to see. Exactly. Right? Internal angles of a triangle are 180. 180 minus 90 is 90, right? So all that's left for these two is 90, so they have to add up to 90. So if I've got a shape that has 4 sides, 90, 90, 90, 90. That's a rectangle. Could even be a square, right? If the sides were all equal, right? If I knew that all 4 sides equal each other, then I know it's a square. But until then, I just know it's a rectangle, right? That's kind of cool. We just proved it's a rectangle. That's like end of semester 2 or middle end. But yeah. Alternate interior angles, right? Whenever you see parallel lines, you should be thinking, okay, I'm going to be able to find out angles here, right? Because there's going to be transversals. Whenever you see a shared side, boom, there you go. The last thing you might want to look out for is, and this isn't really something that you're going to do yet, or at least you shouldn't be. One of the proofs in here had that, which really ticked me off. How many triangles do you see in this drawing? How many? I know the number everybody wants to say. How many triangles do you see? Just here. Oh, I do a thing at the beginning of the semester that's really great, and I didn't get to do it with you guys. It shows that, yeah. I should do that. I'll try to do that one if and when I come back. How many triangles do you see here? Everybody wants to say 3. First triangle is a small triangle, right? Second triangle is this triangle. And I bet you said the bottom area was a triangle, right? Not, it's a trapezoid, right? Or a 4-sided shape, right? So only 2. These 2 triangles won't be congruent. Or did you, where's the third triangle? Did you see another triangle somewhere? These 2 obviously won't be congruent because one's clearly smaller than the other. But notice how the top triangle uses the blue angle, and so does the pink triangle, right? It uses the blue angle. They have a shared angle, right? Reflexive property. You'll be using that later to prove similarity. Oh, okay. Yeah, there you go. Well, not bad, not bad. All right. So look out for shared angles as well, right? That can help you get 2 angles congruent. You probably won't use that until we get to similarity, though. So yeah, alternate interior angles, shared side, and then everything but triple angle and ass backwards, right? HL for hypotenuse. Yeah. If your friends are struggling, I would send them this way and have them watch this video. But of course, I'm always willing to work with them one-on-one like you. So send them my way. But that should pretty much cover everything, my dude. There's going to be examples that they give you where it's like this one. Like they give you a bunch of angle measures. But that ain't no thing. It's the same thing as what we were doing before, right? Like this is an X. Or at least it should be. I guess it's not because that's... Oh, no, that 43 goes with this. I hate this drawing. The 43 is angle T. It's not this angle here. 2 is what's there. And they use numbers for the... God. Use numbers for degrees. Use letters for angles. They're calling that angle 2 and angle 3. Oh, so annoying. But we know this is an X, so these are both 78, right? And if that's 78, this is 43. We can subtract from 180. We get what angle 1 is, right? If I know what angle 1 is, I can add it with 56. I know that's 43. Whatever this is and that is, minus 180 gets us angle 4 because there's a big triangle here, right? It ain't no thing. If you can do this, you can do that. It's just with numbers. You know what I mean? Match up what goes together, think logically, and then like add or subtract to 180 a bunch of times is what you're going to be doing, right? Because triangles add up to 180 and lines make 180. But anyway, that's all I got for you. Unless there's something specific you want to talk about, I feel like I'm pretty good. There's some more examples, like here, but like they're more of the same. Like parallel lines, you're going to get matching angles. You'll have matching angles here, right? They tell you something bisects, so you're going to have 2 sides that match, right? It cuts JE in half, so this and this will be the same. Blah, blah, blah. This is a little weird. We can get back to that, but I don't think you guys are actually covering stuff like this. Because there's like overlap here. And overlap requires you to use things like segment addition postulate and angle addition postulate. And I don't think you guys actually did that. We can go back and look at that if you are, but that's a little more advanced. Not much more advanced, but you know, you've done enough for today. Here it's another parallelogram, right? You've got a this is the midpoint, so these 2 points are sides are equal. We're gonna get alternate interior angles here. Right here, Bisection, which means we're gonna have two sides congruent. We've got an angles that are congruent. We can go and look at this one later if you want. But that was the basics. I don't know. If you've got time and you want to do a couple of these. Okay. Are these the assignments? I'm guessing these are. This is such garbage. I would just write nope on top of this. Waste of time. It really is. This is terrible. It doesn't teach you anything. I thought it might when I started going over the video. I was like, okay, maybe this is interesting, but no, it's just a waste of time. Like there's a shared angle there. Thank you. So Mitchell, what I would suggest is I would go do these assignments the best of your ability, figure out which ones you're stuck on, and then tonight maybe we can meet, and I'll help you with the ones you're stuck on. How about that? Is that cool? Or if you have questions on one of them, like you're like, I'm not sure if I did this right. What do you think? Oh, you sent me it? Oh, how did I not see this? Oh, you just did. Okay. Oh, right. The extra credit snow day. Okay. Worksheet. Page numbers 211. See what page number is this? I have a page number. I just need a page number to figure out what we're talking about. 181. So 211 is like, I don't know, maybe over here somewhere. They're all pretty similar. So Mitchell, what I would do, you have your book, right? You must, because you're doing this stuff. I would attempt these, and then tonight we can meet and go over them. Is that cool? In fact, tell your friends. We can go over them. Okay, cool. Yeah, let's do that. We'll go over them tonight. Make sure you start them, because I won't have time to do all of them, obviously. So make sure that you are doing the best you can. Cool. Numbers and angles. Do you have an example that you could like screenshot and send me, or take a picture of and send me? And I can do that right now. And then maybe give you enough confidence to start it on your own. Yeah, no worries. Take your time. Infinitely compressing the file? Oh no. You can't take a picture and upload it to Discord? Like with your phone or something? That's what you did before. Well, I mean, I guess you took a screenshot. But you should be able to take a picture with your phone and then just upload it to Discord. Interesting. Interesting. Maybe you could email it to me. Here, I'll send you my email over Discord. And when you sent me the email, let me know and I'll flip. Okay. I did send you the right email, right? Yep. There it is. There it is. Okay. So let's pop this on over. Like number 11. And okay, so 13 does go into it a little bit. Not sure how they're gonna make you do this. Like how, like for me, I'm very thorough with my proofs. That way it's always the same and there's no like, well, you can just assume that. You know what I mean? Because then it's like, okay, when can I assume, when can't I? And it feels like magic. So I always make you guys be super thorough until we get to like a certain point where I'm like, okay, here's what we can assume from now on. So I'm not sure how like picky they're gonna be. But let's look at number 11. So number 11 has two triangles. And they're formed like this. So we do have two straight lines. It doesn't tell you that, but TRQ and VRS, those are going to be straight lines, which means we do have scissors theorem, right? Vertical angles. And it says, given angle V congruent to angle S. So let's do this. We'll have those be black angles since I didn't use a color. And TV is congruent to QS. So TV congruent to QS. We want to prove that VR and SR are the same. Not the triangles, but these two segments. So like I said earlier, what we're going to do is we're going to prove the two triangles congruent, even though it's not what they wanted us to do. And then using CCP, we'll get the individual pieces, okay? So for this one, the first thing we should notice, and I already pointed out, is that we have vertical angles here. Obviously, that means the top and bottom will be the same too, but I don't care about those angles, right? Because those two angles aren't part of our triangles. So angle TRV, always use 3 letters to label your angle. I know it says like angle 1 and angle 2 here, right? Don't use that. Don't use that. That can be confusing. Just call it TRV. TRV or VRT. That will be congruent to angle SRQ. And pro tip for your angles, when you draw them, try to have that bottom line be horizontal. So like when I draw an angle, I always make sure my bottom for that angle symbol is completely horizontal. Okay? That way it doesn't look like a less than symbol. So now we're here. And we want to prove that some segments are the same. So first of all, let's get the triangles congruent. So Mitchell, triangles. How are they congruent? Do we have enough information? Looks like we've got two pairs of angles and a side. Yeah. So by angle, angle, side. Triangle. Let's do alphabetical for this one first. QRST, right? So RTV. As in rock the vote. Will be congruent to this triangle, second triangle. R is going to go with itself, right? Because they're both the green angles. T is the unknown angle, so it's going to go with the unknown angle here, Q. V, let's see if I can get this thing to focus. V is the black angle, and it goes with S. That's what we already said, right? So now that I have those two triangles congruent, then I can use CCP, right? If the triangles are congruent, which they are, I proved that, then I can use CCP. By CCP, I can match up parts. I can say that RT and RQ are the same. That's cool. I can say that RV and RS are the same. I can say that VTR and RQS are the same. VTR and SQR. Third, second, first. Reading it backwards, right? They're going to be the same. These angles here. But what I want to prove is that VR and SR are the same. So I'm going to look at VR. VR is third and first, right? So it should be congruent to SR by CCP. Ta-da, VR, SR, I win. Black box. Ta-da. I don't know. I don't like using angle 1 and angle 2. I'd just rather use the three-letter name for this instead of calling this angle 1 and this angle 2. I think that gets confusing. How do you feel? The next one's harder, and this is one of those ones that I thought we could avoid. For 3 triangles. For number 13, there's more than 3. First of all, let's play a game. This is the one I wanted to avoid because it takes a little bit extra work and a little bit more understanding, and I thought like we'd keep it simple for the first time you're doing this, right? But it looks like we've got to catch you up a long way. So for number 13, let's look at this. Here's our diagram. First of all, how many triangles do you see here? You said 3. There's more. 1 big one. 2. 3. 4. 5. This whole thing here. 6. This whole thing there. It's a lot of triangles. So they say given. Let's do letters first. So L, M, N, E, Q. They say given that MN is congruent to PQ. So that's this and that's that. Okay. And we're also given that angle M, let's do blue. Angle M is congruent to angle Q. Now they're only using single letters here. Yeah, I know. And diagrams should be big, period. That's why I always make my own stuff and I make the diagrams gigantic. And it takes forever to draw them, but I do it. And I do it with a computer. It's beautiful. I love teaching geometry. So they only use the single letter here, which is fine because there's only really one angle M in the triangle. However, this is also angle M, this outside angle. So I don't like using that. Obviously, like, for N, there's multiple angles going on here, right? So I just like students getting in the habit of using 3 letters, call it L, M, N, or N, M, L, right? But whatever, that's what they're doing. So these 2 angles are congruent. I think it's just another way to confuse you guys. Then it says angle 2 and angle 3 are congruent. Oh, God. Okay, let's convert that. Angle 2 and angle 3 are these 2 angles. Okay, so let's just convert that. That's angle L and P. They're like, let's call those numbers because we don't want to use 3 letters. Just use 3 freaking letters. LNP, LPN. Cool. And we want to prove which 2 triangles congruent. MLP. Oh, God. Okay. So I'm going to trace. Ooh, it's my last piece of graph paper. Gotta go back and get some. So LMP is this triangle. We want to prove this triangle congruent to triangle QLN, which is this. Okay. Those 2 triangles, the 2 medium triangles that I pointed out earlier, right? That's what we want to prove congruent. So this is very advanced because it's hard to see, right? Because there's so much overlap, right? It's not going to be harder, but it's going to be harder to see. So in the yellow triangle, I already have this angle and this angle congruent between the yellow and the purple. And I already have the left angle here of the purple triangle congruent to the right angle, the right side angle of the yellow triangle. So obviously getting another angle isn't going to help because triple angle doesn't do anything for us. So we need to find a side somewhere, right? Now we have this, but notice this little bit is not an entire side of our yellow triangle. So it's not very useful, right? All we know is this little amount and that little amount are the same, right? But that's not a whole side of this triangle, right? So here's what we need to do. We need to figure out an entire side of one of those triangles. Here's my logic, okay? Here's my logic. That side is the bottom of this yellow triangle, right? MP equals this piece, right? MN plus this piece. Let's have that be purple. NP. Are you following me so far? Right? This whole thing is 2 segments added together. This is segment addition postulate, right? The pieces of the segment make up the whole segment. Okay. Segment addition postulate, something we did super early in semester 1. These 2 segments, when you add them together, make up the whole thing, okay? Right? That's not anything crazy. That's pretty straight logic. I also know by segment addition postulate the same thing here. So let's say this. NQ is going to equal PQ plus NP. I'm going to do the same color because I'm talking about the same thing. That's by segment addition postulate, okay? Now check it out. If the bottom of the yellow triangle, this like mint color, right? If that's black plus purple, or pink, I guess. Let's do pink. Black plus pink, right? These 2 bits. And this bottom of the triangle, the peach bit, is black plus pink. What does that tell you about the relationship between mint and peach? What does that tell you about the relationship of mint and peach? How do they relate? Exactly. They both equal the same thing, so they equal each other. So we know that this equals that. Or in other words, let's make it congruency, right? Let's talk about the actual line segments. And what we just did here is we did substitution. Okay, hear me out. This equals that, and that equals that. Do you see how peach equals this? And since that's the same as that, I can take this and switch it out for peach. So I took this statement, mint equals this stuff, and changed it to mint equals peach. Because peach is the same thing as that, right? So I switched them out. Substitution. Like the substitute you have in class right now, right? They're basically the same as me in every possible way. So they switched them out. Joke. Are you smelling what I'm stepping in? This is a new idea, substitution, right? We kind of use it in algebra a little bit, right? If x equals 2, whenever you see an x, you can plug in 2, right? Well, if if this equals nq, whenever I see this, I can switch it out for nq. So I saw this and switched it out for nq, right? And that's how I got this statement. That's what you did when you said they must be the same. This is just the reason behind it, okay? So by segment addition postulate, I set this up. And then by substitution, I can switch it out to get what I want. So now I've proven that this part is the same as this part. So in other words, I have two angles and the side in between them. And I have two angles and the side in between them. So now I've got by angle, side, angle. Oh, yeah, 'cause you can't see. Angle, side, angle. Triangle, left side triangle is MLP. Actually, I do in alphabetical order, LMP. I like alphabetical. LMP. To be congruent to, L is going to go with itself because M goes with Q and P goes with N. We win. So harder because of two things. One, it's a lot to see. Tracing can help. And two, it has these two new things that we haven't really talked about in a while. Segment addition postulate, right? Using the pieces to get the whole thing. And then substitution. Switching out ideas that are the same, right? That's how you handle a beast like that. Does that feel better? It shouldn't feel great because this is difficult. Like, these are some of the more difficult problems I give in this, like, I guess you can call it unit or whatever, you know. When I did my quizzes last year, this one was difficult for people because seeing that you can do that is difficult, right? And it's because they both share NP, right? Something plus NP will equal the same thing plus NP, right? So these two bits are the same. So we have angle, side, angle. How do you feel? When there's partial overlap, you're almost always going to use segment addition postulate, right? Anything else for me for now? Or do you want to go give it a shot? I mean, go eat lunch or whatever and then give it a shot. And then come back later tonight. What do you think? Head on out? Okay. Okay. What else you got? see if I can find it. Position and label each triangle in the coordinate plane. What? Okay, let's see if this has educational value. Let me go grab some graph paper out of the back room. For that printer, start printing my own. All right, so this is from the back room, so it's like really crappy graph paper that I didn't use in last March because it had like junk on it, which is like a coffee stain here at the bottom. But we'll use it; it'll be fine. Okay. So it says an isosceles triangle with base QR that is b units long. Okay. So here's a coordinate plane. Base QR. We'll say it's b units long. And it's isosceles. So you know as well as I do that if it's isosceles, the two side lengths need to be the same. So I'll just go to the middle. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 1, 2, 3, 4, 5. I don't know. I'll just go up as much as I want from the middle. But that's isosceles. And the reason I know that is because it's 4 over, right? And it's the same amount up for both, right? So Pythagorean theorem would say that 4 plus whatever squared plus whatever this is squared will get us this length. 4 squared plus whatever this is squared will get us this length, right? Has to be isosceles. So QRT, and then you can just write down whatever those coordinates are, I guess. I don't know. Ta-da, there it is. Did you see my logic to make sure that those two were the same length? I just reverse engineered it. I said, if I know that's 4 and that's the same for both, then these lengths will be the same, right? That's kind of what we were doing earlier with like the distance formula thing. Are you okay with that? I don't know. B in this case would be 8. Okay. Well, they're saying make your own, essentially, which is fine. Like, if I was being cheeky, you know what I would do? I would do an equilateral triangle. Because equilaterals are isosceles, right? All the sides are the same. 2 sides are the same? Yeah, it's isosceles. It's just better described as equilateral because it's all of them. The next one says equilateral triangle with sides 2a units long. Okay. Like, what would I do for that? An equilateral triangle 2a. So we need everything separated by the same amount. So to make it nice and easy, let's do something like this. Let's do square numbers. So let's have every side be 4 in length. So there's a length of 4. 2a. I don't know. And then to get a length of 4 here, actually, you know what we should do? Well, actually, we wouldn't use ptheg. Well, we would use ptheg in this case, I guess. 2 and 2. 2 squared and 2 squared, that's going to get us 8. So that's going to be an issue. Ah, I see what's going on here. Okay, so this is going to make you think outside the box. So some of these lines are going to have to be like diagonals, right? And so if we have a diagonal length of, let's say, 16, let's do this. The diagonal length of 25. Four and 9. Well, that's 4 and 9. What am I doing here? 3, 4 is what I want. So there's 3 squared, there's 4 squared. That's going to be 25. That's 25. So if I have side lengths of 5 all around, this should help. So let's see. 1, 2, 3, 4, 5. And then since this is 5, I can go in 3. Wait a minute. Interesting. If we want to equilateral, how do we go about doing this? This is harder than I thought. Not impossible. But how do I teach this quickly? And what are they trying? Like, what are they trying to teach here? So if I start one of my coordinates on 0, 0, right? This is M and P, so M. And let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's go 10 out. There's N. So that's 10, 0. This is 0, 0. Where does P have to be? Well, yeah, but you're going to do your best, right? Where does P have to be? This is definitely the hardest one, like one that we haven't talked about yet. Well, it'll have to be in the middle of these two, and it'll have to be the same distance on both sides. And it'll be the same distance as this. So this is a distance of 10, right? So it'll have to be the same way. It'll have to be halfway through. 1, 2, 3, 4, 5. There's a halfway point. There's a distance of 5. And then we need to do ptheg in such a way that this ends up being 10 as well. Like this length here. So 10 squared equals 5 squared plus what squared? That's going to tell us how tall this has to be, this bit right here. And that's how high we'll go up, and then we'll have 10 on every side. So 100 equals 25 plus x squared. Subtract 25, 75. X is going to be root 75. So we're going to go up root 75. Now I know 64 is 8, right? Root 64. And 81 is 9. So it's somewhere between 8 and 9. So 1, 2, 3, 4, 5, 6, 7, 8 and a half-ish. So I'm going to say that coordinate is 5 to the right and root 75 up. And if I were to connect the dots, all these sides will be 10. So what I did was I picked some length at the bottom, something that's easy to divide by 2. And so I said length of 5 here, right? Because it's got to be halfway in between these two dots, right? And the question is, how high does it have to go up so that this is also 10, right? So my thought was 5 squared plus what squared gets me 10, right? 10 squared. And it turns out root 75 is how far we have to go up. Not a nice number. I was trying to make it nice earlier, which is what made me into a funk. But like that's what I would do there. Did that sort of make sense? Are we okay with that sort of? Right, I picked 2 spots, really easy. Made a length, went halfway, and then figured out what this has to be to make that also the same length as down here. Yeah, this is interesting. I'd like to see the instruction for this, like who taught this and how they taught it. Because then I could maybe figure out like why they're having you do this. Like they're not like bad problems because they're like there's like a challenge here, but I'm trying to figure out like why they chose this out of everything else. Okay. Out of all the things you could be doing, why this? You know what I mean? Especially for kids that seem like they're struggling. Isosceles right triangle with hypotenuse JM and legs C units across. Okay, so here for the plane. Teaching on a video. Can you send me those videos? Is there a way to do that? Because I'd like to see what's going on here. Maybe I can help you out later. So JM is the hypotenuse. Okay. So let's make this L. Make this J. And the hypotenuse is JM. So let's make that M. There's our right triangle. Okay. Something like that. And legs C units long. Okay. C. If they want to give like specific coordinates, position and label each triangle on the coordinate plane. I guess we could do that. So how do we make these two the same length? Well, let's say that's at 0, 0. Let's say that's at 10, 0. And that's at 0, 10. Ta-da, distance of 10, distance of 10. I don't know. Does that make sense? How'd that one feel? They said JM had to be the hypotenuse, so I made sure that JM was across from the 90 degree. I'm not really sure. I'd like to see somebody teach this. That way I can figure out why it's important. Okay. All right, next one is equilateral with sides half of B units long. I mean, do this and have B be 10. Change the letters. I don't know. It's an equilateral triangle. You see what I'm saying? I already have an equilateral triangle. B is 10. The sides have to be half B units long. Oh, sorry. No. Have B be 20. All right, B is 20. And so the side is half of B. And I don't know. There you go. Isosceles with a base that is A plus B units long. Dude. Isosceles, the base. A is 4, B is 4. Done. Yeah, I'm not sure what the point of this is. Right triangle with hypotenuse XZ. Okay, call that XZ. And ZY is double XY. So this is twice as big as that. Okay. Shrink that down to 5. Well, these ones aren't. These ones definitely aren't. Like, ta-da! I did what you asked. It's that triangle now. This is twice as big as that. I don't understand. And then the last one you sent me. Let me take a look at that. Yeah, it seems like they're like trying to have some interesting questions here, but they're really just more confusing than interesting. All right, let me check out the last bit. Oh, you sent me the video? Okay. Cool. Yeah, if you can send me all the videos on that, that'd be super helpful. Because then I can figure out exactly what you guys are learning, and then when we meet tonight, I can help even more. But yeah, I would save these for last. I mean, I basically just did them all for you, but I would save these for last. They're not very interesting or very useful. I would do the other ones. Take it a little bit at a time, Mitchell. Don't worry about like having to get all the homework done. The goal is just to get as much as you can. Oh, okay. Well, I'd ask her to send you those. Just so you have them. You know what I mean? But like, yeah, focus on one assignment at a time, because the goal is not to get them all done. I mean, like in a perfect world it would be, but really the goal is just to get as few zeros as possible, right? So start with one, you know, keep going, and take breaks. You got to take breaks, man. So today, yeah, it's going to be annoying. Most of your day is going to be spent doing math because it looks like a lot of assignments that you just didn't do the last couple of weeks or whatever, which no shame, right? That happens, man. It's a freaking pandemic. But like do one at a time and then take a break after each one. Guaranteed break after each one. I know. You have to take a break after each one. Doesn't have to be a long one, but it has to be at least 30 minutes, okay? Has to. It has to. Otherwise, your math is going to suffer and it's going to be a waste. It really will be a waste of your time, okay? 30 minutes minimum after each one. If you want to take breaks during, that's okay. Take for like 10 minutes or so. But definitely 30 minutes in between each assignment, okay? Definitely. And you might be like, oh, that one was easy. I'll do the next one. Take 30 minutes because the next one might be hell. And now you've done one that's hell plus an easy one, making it even more stressful, right? Always do 30-minute break. But yeah, give that a shot, and then we'll meet tonight, okay? What time do you want to meet tonight? Well, actually, you tell me on Discord, okay? We'll figure it out. I'll talk to you then. Is that cool? Take a 30-minute break starting right now. Go eat some lunch and stuff, and then get into it. All right, I'll talk to you later tonight. Take care, bud.